from EC Illinois, James Yang. Please help me welcome him.
Hello. Yeah. Hi, everyone. My name is James. Thanks for coming to my talk. And my advisor is Professor Hayek. And today I'll be talking about distributed content collection and recommendation. So it's a distributed system where content collection and recommendation are done jointly. So this is an overview of my talk today. So to give you an idea of what this is in everyday life we're faced with many decisions that could be movies to watch, deciding what restaurants to visit, books to read, and etc. But to make good decisions, that usually comes with taking good advice. So one way of taking advice in a centralized way, where there is a centralized authority that takes our personal information and processes them in some way and gives us back a recommendation. But we can also do this in a distributed way, where, for example, like word of mouth, where some of your friends maybe recommend you something that they personally like, and after listening to them, you decide what advice you should take. So what we are going to do, we're going to study a distributed system where we're choosing videos to be collected and also recommendations to be given jointly at the same time. To illustrate how our system proceeds is we have a black peer over here and a red peer over there. And each peer initially start out with some videos. The videos are highlighted with colors, and they are ordered according to their preference. So the left one is more preferred. So before a peer actually watches the video, he doesn't know whether he likes it or not. So in here, the black peer contacts the red peer, and then figures out that he might like the green video, and then he downloads the green video and watches it, and then he figures out he likes it the third best among all his watched videos. So he downloads that and inserts it into the third spot. So the system proceeds forward, and the black peer contacts a blue peer in the next time step, and then in this time he prefers the orange video and watches it and figures out he likes it the second best. So that's basically how the system proceeds. So to simplify our analysis, we're going to assume a closed homogeneous system where the number of videos and peers are fixed. They proceed in a synchronized time step, and where each peer contacts another peer uniformly at random, and they start out with some videos, C number of videos uniformly at random. We assume there is sufficient bandwidth so that in each time step, only one video is being downloaded and watched. To measure performance, we're going to assume a happiness function that assigns higher value for more preferred videos. So the objective is then to drive the normalized total system happiness to 1 as quickly as possible. So to model preferences, we're going to use a correlated scoring model where we assume some hidden variables called the master scoring function that assigns a score to each of the video. Then the personal scores has the following distribution, and they're conditionally independent. We call this the independent crossover channel, and it is with a crossover probability matrix W, which is generated using the Plackett-Luce model with a zip distribution, which is usually used to model popularity. Then the happiness function for each peer would be, over a set of videos, would be the following. So before going into the recommendation strategies, I would like to study the upper bounds for the system performance to draw some insight before designing what algorithm to choose. So one trivial upper bound is if each peer knows what he personally likes and just downloads the videos according to his personal taste from a central server, assuming the videos are available to him. But we can also find a tighter upper bound, which can be achieved if a peer knows the master scoring function, which is just the hidden variables, and downloads according to the scores from the master function. And this follows from the following result, which basically says if each peer downloads according to the master scoring function. So basically, if the personal scores are generated from the master scoring function with Plackett-Luce with ordered parameters, then the personal scores of the videos are stochastically ordered with respect to the master scoring order. So what we obtain from this theorem is that if peers are downloading, then the peer will be better off if he downloads according to the master scoring function. So if we design a recommendation strategy, then we would like to have the peer use some method to estimate the master scores and downloading according to the master scores, which leads us to our first recommendation strategy called the maximum likelihood. Here, each peer is going to collect all the preference information of all the past contacted peers. Then he uses a maximum likelihood estimation to estimate the hidden variables, which is the master scores, and basically downloads according to the master scores in each iteration. So this one, as you can see, it's more computationally intensive because he is collecting as much as preference information as possible. So he's basically emulating the centralized server. But we can also, in contrast to the previous one, we have also a simple model which calls direct recommendation strategy. Here, the peer is simply just going to ask what the contacted peer likes best that he hasn't watched already, and then he downloads according to what the contacted peer likes. So to visualize these two algorithms, we have simulated the distributed recommendation system with 1,000 peers, 1,000 videos, with each peer having a cache size of 100. And the uniform, and we use the performance metric to be a uniform happiness weight for the 50 top video out of the 1,000 videos. As you can see, it is plotted, normalized total system happiness is plotted against time. On the far left-hand side, you see the ideal upper bound where each peer is just downloading according to his personal taste, assuming he knows it. So the tighter upper bound is the red curve over here, where peer is actually downloading according to the master scores, which is the hidden variables. But as you can see, for the first recommendation strategy, the maximum likelihood estimation, the performance nearly matches the upper bound exactly, which tells us that the peer is doing very well in estimating the hidden variables. But looking at the second, which is the simplistic algorithm, we see the direct recommendation also does pretty well in terms of how close it is to the tighter upper bound. So what we get up to this point, what we found is that first, we know that each peer would be better off downloading according to the master scores. So the first algorithm is going to mimic that by collecting a lot of information and estimate the master scores. But what we are really, what's really interesting is that the direct recommendation strategy that we found is very simple. Basically, just not storing any of the previous partial information and just listen to the contacted peer at this time, and then and it is found to be near optimal too. So what we would like to do next is just to analyze this direct recommendation strategy in more detail. So for the second half, I'm going to analyze the direct recommendation strategy. So to analyze this, we're going to keep track of the states for each peer. As you can see, for each video of each peer, there's L+1 possible states. L states for one of the possible scores, and one additional state for the video hasn't been downloaded yet, which is 0. So we let X represent the state of a peer n at time t. And the empirical distribution is calculated as follows. Then each peer state transition probability is given as follows. So as you can see, there's two problems with analyzing this system. One is that the state space is very large. It's exponentially growing in the number of videos. And the second problem is the empirical distribution. This is the state transition probabilities, which means it's random in terms of how peers are contacting with each other and how their state is transition. So we would like to simplify this by doing the following reductions. The first reduction is applying Kerr's theorem, where we let the number of peers go to infinity. What this says is If we let the number of pairs go to infinity, then the empirical distribution the empirical distribution's dynamics becomes deterministic. So mu would be a empirical distribution, would be a distribution for the S states. And then you follow the following dynamics, and this dynamics, and then the empirical dynamics would be in the asymptotic regime would be deterministic. So next, after making the evolution of the empirical distribution deterministic, the size of the state space is still very large, so we would like to reduce the number of states. We do this by exploiting some of the properties which include a symmetry property and also delayed exposure of information, because each pair has their scores generated from a parametric model. So in the end, as a result, it suffices to just track the number of states. It suffices to just track the reduced states, which just says how many videos that each pair has for each master score group. So as a result, the size of the state space has been significantly reduced. But the problem from the previous one is that even when we have reduced the size of the state space, and also we have found a deterministic evolution of empirical distribution, then to actually calculate the evolution or the dynamics, which is we use the previous this equation, this state transition probability is still very hard to compute with that many states. So next, we're going to reduce this further by allowing the number of videos goes to infinity, thus fluidifying the videos. And here, once we do that, essentially law of large number applies, then we have a concentration result where the empirical distribution concentrate at each time. So what this tells us is basically we can simplify our entire model, reduce the number of state space, and calculate the dynamics evolution by reducing it to the following differential equations. And there's an intuitive interpretation of the evolution of each state is inside the bracket in the numerator, it would be saying, suppose you're looking at the number of videos in master score group K, then inside the bracket would be the fraction of the video that you don't have yet, multiplied by the fraction of the video that the contacted pair has it, and also by the probability distribution that is given as a score 1. So out of all the videos that are recommended to you. So by calculating this, by solving this differential equation, we get this equation, and also along with its initial conditions where we can calculate out the result or the dynamics of the empirical distribution exactly. So finally, to illustrate what this is we also compare this result with the previous simulated result, also in the same simulated distributed recommendation system with 1,000 pairs, 1,000 videos, and also the same parameters. As you can see, the blue curve which matches the green curve is actually the one that is being calculated from the mean field limit. And so basically, to sum up the talk, we have on the second half of the talk, we have first discussed how the evolution of empirical distribution can be deterministic by applying the Kurt's theorem. Then we reduce the size of the state space by exploring some of the properties. And finally, we let the number of videos go to infinity and reduce the problem so that we can calculate differential equations, a set of differential equations. And finally, from the plot, as you can see that the calculated result matches the simulated result exactly. And that concludes my talk. Thank you.
We have time for one or two questions.
So in the end, your group is
We didn't prove that it's near optimal, but we proved that in an asymptotic regime that it can be calculated to be exactly the same as. Oh no, it doesn't meet the upper bound. There's still a gap inside. Yeah.
So you conclude it's not well.
Well, yeah. The conclusion doesn't say it's.
It can still be optimal.
Yeah. In the model parameters that we chose, it appears to be near optimal, but we haven't proved that it's near optimal in any sense. But
It's not exactly optimal.
yeah, it's not exactly optimal.
Maybe the upper bound can be improved.
Yeah, possibly. Yeah.
Just want to know if you have made connections between your work and the literature on voting. It sounds somehow similar. You have peers, reviews, preferences, and they got voters, candidates, again, preferences. You have happiness function. They've got social welfare.
Yeah, we haven't thought about voting.
You have that score function you have.
Right.
It sounds very similar to potential gain among the voters, actually. I just wanted to know if there's connection.
Yeah, we'll have to think about that. Yeah, we haven't thought about whether.
It's related. The difference here is you've got a very large number of videos that you're passing around. Everybody is simultaneously scoring and collecting the videos.
Yeah, but I would be happy to talk to you
You're
afterwards.
also not reaching